her slides and get us started.
Great, thank you so much. Let me just get this started, and hopefully you can see my screen. And I'll go into presentation mode.
Perfect, yes, we can see it, thank you.
Great, it's just a little delayed on my end. Perfect. So thank you so much for organizing and for inviting us all to present our work. Today I'm going to be talking about some of the work that we've been doing, looking at distributed decision making and specifically distributed optimization, and how that can be used to flatten what we call the duck curve. So this is predominantly under themes 3 and 6. And under my PI, Anu Anaswamy, we've been working overall on the UI assist in themes 3, 6, and 7. So just to get started, I wanted to just share some of these newspaper articles and their titles. And this is just to kind of set the stage for the kind of conversation we're having. So September 2021, we had the Biden administration talking about having a 45% solar power generation by 2050. We have US hybrid electric cars in January 2022 reaching record highs. And then we have this idea of moving towards the Internet of Energy. And the reason I bring these up is just so that we can kind of understand the main driving forces for the work that we are all doing and how in my work I am looking at these aspects. So we're looking at decarbonization and the shift away from predominantly fossil-based energies towards cleaner energies, for example, solar power. But along with the large grid scale devices, we also have a lot of customer adoption of smaller devices. So this could be solar PV on the rooftop, it could be EVs in the household, it could also be kind of larger storage units like community batteries or Tesla power walls. And that's what I'm going to be looking at a little bit more today in the work I talk about. And finally, we have the ability to use these kind of distributed energy resources or DERs through what we call the Internet of Things, and it's kind of been affectionately being called the Internet of Energy when applied to our smart grids and smart systems. So with these three big drivers, the other thing I want to touch on is where these come together in the electricity grid. And so within the distribution grid, we're looking at a very DER-rich grid edge. And as we have kind of these huge number of nodes, so suppose an urban distribution network having 2 million nodes, if we imagine each of these nodes having at least one DER, all of these devices together and that large amount requires some amount of distributed computing. And so at the grid's edge, we are seeing increased intelligence and control through smart meters, and we have more renewables, so we have more control units. But we also have communication enabled between these devices, and we have faster timescales. So demand response, as we know, can react quite quickly. We have quick fluctuations in solar production. And so all of that points to this need for resource coordination through optimization is what we're looking at. And the paradigm for this has to be fast and distributed. So with that, when we're looking at distributed decision making, there's really three kind of components within the work that we do. We have our electric grid layer. On top of that, we can imagine devices that are put throughout the grid, and we can kind of have these clusters of devices if we need to. And then we have some kind of communication layer, especially within a distributed architecture. So for the electric grid, we're really looking at moving towards physics-aware decision-making. So being able to model the underlying distribution grid, the constraints on the system and the network losses, and having the decisions that we make from an operator point of view, have those taken care of and those constraints being part of the solution. And so when our DERs are making decisions, they're aware of the physics and they're able to model this. And with the devices, we also get more operational flexibility to be able to kind of turn knobs at different points in the system. But because they are privately owned, it changes the kind of decision making that we are able to do and what kind of architecture we might want to be using. And finally, because they are privately owned, we might want to be able to keep privacy of data. And so rather than sending all data towards a central location, you might want to be able to have distributed decision making. But if you still want to reach a global objective, you would want to have coordinated decision making, and peer-to-peer communication really enables us to do that. So with this architecture, we're going to see this come again throughout the presentation as we kind of break down into these different components for our problem. So what we're really looking at is a physics-aware distributed coordination of devices. And so this first component, as I mentioned, so we're looking at the physical layer of the grid, and that'll be our first model. Rather than using some of the more popular power physics models like the branch flow model or the bus injection model, we wanted to look at a model of the distribution grid that is able to model the three-phase unbalanced nature of the grid without requiring kind of bounds on the angles and balanced assumptions. And so we have come up with a current injection model. And so we're coming back to the definition of kind of how rather than looking at power injected at a node, we're looking at the corresponding current at the node. We have our Kirchhoff's current law and Ohm's law. And just the definition using those relationships are number 3 and 4, which are the real and reactive power at a node. And when we look at these are actually non-convex constraints because they have bilinear terms when you expand this expression. And so we take the route of convexifying these non-linear, non-convex equations into linear convex equations, and we're using McCormick envelopes. So if you can imagine, one Pj is going to be a sum of 2 terms, and each of those terms is going to look at something like x times y. And so rather than modeling that black line, which is that exact nonlinear, non-convex structure, we're looking instead at this entire green and red shaded line, and that's the convex hull of that term. So we now have a linear and convex relation, and by introducing the McCormick envelope, we need 2 things. We need the bounds on the voltage and the bounds on the current. And the bounds on the voltage are quite simple because we know them from operating the grid. So we have maximum and minimum, about 5% deviation in the US. And the current bound we can actually calculate through a specifically designed pre-processing, which uses information about the forecasts of real and reactive power injection and the voltage bounds on the network. So with all of that, we are able to come together to have our full current injection model. And the current injection model is a linear convex model. And so we can use this to really minimize any objective functions. So we could be looking at Volfar control, social welfare, which is in the context of energy grid, retail markets, and we can look at cost minimization. So we can extend this to multi-phase grids by simply just modeling each of the phases. And because we have our relationship with the impedance here, it's fully able to model the unbalanced nature. And when compared to ACOPF, we get quite good performance. So we're seeing 1.2% optimality gap performance and 0.9% voltage error gap. And that's compared to the original nonlinear formulation, which we solve with a nonlinear optimization solver. So with that current injection model, we want to move into this third step. And the second step is going to come from our application to the flattening the deck curve. So when we're looking at that third layer, we're really looking at our distributed optimization. And we've presented our PAC algorithm previously in other UI assist meetings, but I just want to go over it really quickly. So our underlying model is this optimal power flow, and we're looking at 3-phase unbalanced, the linear current injection model. And then we have our model for our constraints. The objective could be different objectives. Here, for example, I've written voltage control, and for our duck curve example, we're going to see different objective functions, which I'll get into. So with this model, this global model, we can essentially break it down so that every agent in the network has its own local optimization problem, which it solves, and through communication with its peers, it's able to come to the global optimal solution, which is the optimal set point for our distributed devices. And so our PAC algorithm is computationally tractable because it's distributed. It has reduced communication requirements compared to some other distributed algorithms, and it preserves data privacy, which I'll talk about in the next slide a little bit. So the algorithm looks like this, but I don't want to get too detailed into the math. But I just want to mention that we have been able to show that it converges, and it theoretically converges, and also in simulation we've been able to show this. So when I mentioned data privacy, this is something that's very important for a lot of our applications, especially in the smart grid, where, as I mentioned, the DERs are privately owned by various different agents. So there's 2 kind of key features within the PAC algorithm that I want to mention. So the first is what I've highlighted in purple, and that's an acceleration on the dual variables mu and nu. And that acceleration basically allows us to achieve better performance for our convergence, and that comes from a predictor corrector regularization. Now, the component where we are able to now use that acceleration towards data privacy is here you see this gamma j and then the gamma j hat. So basically we have a time varying term, so it's tau plus 1 every iteration, and we have an atom varying. So every atom j will have a different gamma value. And just by having that time varying and atom varying gain, we're able to preserve the privacy of both of these dual variables. And so if we're really looking at what the exchange of variables between one agent to another looks like in the PAC algorithm, the local variables would be AJ, and so that would be kind of like your power set points and things like that. And then your coordination variables nu, which we need to share in order to converge to the globally optimal solution. Rather than exchanging nu j on its own, we're exchanging this nu j hat, and that's basically a masked dual variable to be able to retain privacy. And this is really important because these dual variables are shadow prices and can reveal sensitive information about operating constraints. So in our algorithm, this is fully private. Now, coming back to what we had as the current injection model, when we take our current injection model, which we have on the left, we can apply the PAC algorithm to it, and so we can atomize this problem and basically break it down into what every node would see. So this is what the global variable vector would look like. You have your currents, voltages, real reactive power, and then A, B, C, D are your constants, sorry, not constants, your variables that were introduced for the McCormick envelope relaxation, and then we have our current flow across the lines. The first coupling constraint is Ohm's law through our nodal voltages, and so we basically retain copies of downstream variables, and the state variable is the nodal voltage itself. And the second coupling constraint is KCL, so Kirchhoff's current law. And so that would be your branch currents. And so we basically just retain upstream branch flow copies, and we keep the downstream branch current as state variables. So with this, we have fully distributed our current injection model, and we can run PAC with it. So the last component I want to talk about is the application of our CI model for our unbalanced distribution grid and our distributed PAC algorithm towards this case study, where we're looking to flatten the duck curve. And so this is a very characteristic profile from California. If we have our solar generation and our total load in blue, our net load would look orange. And so this is affectionately called the duck curve because you see this looks like the belly of the duck. And then as we come here, that is the head of the duck in the evening. And essentially this fast ramp that you see, that requires very steep ramping from our conventional generators in the bulk system. And we're interested to see if we can use the DERs in our distribution grid to help alleviate that and reduce that ramping at the bulk level. So we're looking at a modified IEEE 34 node network to be able to model our distribution grid and see if at the point of common coupling in node 1, we can use the resources throughout the grid to help alleviate some of that ramping requirement. In our network, we have a variety of different residential and commercial loads, and these were chosen so that we have varying demand profiles throughout the day and chosen based on the original IEEE data. So larger loads would correspond to, say, commercial loads, and smaller load points would be residential. We have 3 battery units at 6, 19, and 27. And then we have various DERs, so demand response and solar PV distributed throughout the grid. So points where you don't have load, it probably has a PV unit in that network. So it's a very high penetration, 38% penetration, nameplate capacity of PV units. So we've talked about our problem setup, which is our physics model and the McCormick envelope relaxation in our CI model. The second layer was our devices, which I introduced in the previous slide. And the third layer is our distributed algorithm. One small difference I want to mention in this paper is that we're using an accelerated variant of our PAC algorithm. So we're introducing a Nesterov type acceleration and also some enhanced privacy characteristics. So it's able to converge faster, but it also has some additional privacy of the primal variables. So including the dual variables, which we have in PAC, we now have privacy of the primal variables, which could be your power, voltage, currents as well. So with all of that, to be able to kind of compare what distributed control can get us compared to, say, another baseline, we're looking at both local control and distributed. So in local control, every node, or in some cases groups of nodes, have their own decision-making schemes, and there's no communication between any nodes. You can see a couple of groups here, and the reason that we've created some kind of clusters in this scheme and still called it local is because of the battery units. If a battery unit were to operate kind of on its own without any information about the rest of the network, it wouldn't have too much ability to actually act in the network. And so by creating some of these clusters, we rather instead have a cluster of loads and a battery that are then able to use that battery to its advantage. Every agent, so 7, 8, 9, they're each individual agents, and this would be one agent together, for example. They have a local objective, and this is somewhat of a selfish objective. So it's just to reduce the peaking at that node. So we have a community battery, a hospital battery, and then a cluster of Powerwall, Tesla Powerwall batteries. And so these battery units are also present in our distributed control along with the PV and the demand response units. But in this case, every single node has its own decision making, so we don't have any clustering. There is communication between the nodes, and that's according to the PAC algorithm. And we're using coordinated decision making to reach a global objective to minimize the ramping at the node 1. So from our 3 scenarios, we also consider a baseline where batteries and flexible loads are not present. And so we only have our loads consuming at a set amount, and we have our PV units generating at full capacity real power. And then we're comparing with local control, which the communication graph would look like this, and then distributed control where the communication graph exists. So there is communication between the nodes. The objective function looks a little different between the two. So for local control, every agent is trying to minimize the daily peak load. And this is a reasonable proxy for kind of minimizing the ramping from hour to hour across the network, because that highest peak happens in the evening. And if you're able to alleviate that at every node, then you can kind of think about that as a global effect, alleviating the cost on the network there. And another approach to thinking about this local objective is that a lot of bigger loads will be billed some peak amount, so a peak charge. And so if you're able to minimize that peak charge over a duration of time, that's beneficial for you as well. Our distributed control is a much more global approach, so it's trying to minimize the hour-to-hour demand at the point of common coupling. And as you see, both of these are coupled constraints, and they're multi-period constraints because of the storage, 1, and number 2, the objective function itself is coupled over time. So we're taking a multi-period approach with rolling horizon. So say we're looking at 5 time steps. We will optimize over 5 time steps, actuate at 1 time, and then slide the window over, optimize over the next 5 time steps, actuate, and then continue that way. So in our results, we have the net load serviced by the bulk system shown here for the baseline in blue, local control in red, and distributed control in yellow. And I just want to point out a couple of key things. The first and the obvious one, which I have the arrow to, is that the distributed control is able to reduce the ramping needs up to 23%, whereas a local control in comparison isn't actually able to do this. So if you look at this, this peak is lower than the blue. And so you do have some impact of that objective happening, but you're not able to leverage the resources you have throughout the entire network in order to get the kind of improvement you see with your distributed control. And so really in our system, distributed control is what you would need in order to enable these DERs to provide a bulk level support. And so some of the key takeaways that we have here is the idea that our small-scale DERs can be coordinated to provide bulk level support. We do need to be able to model the grid physics so that the system constraints can inform the decision-making, and we're readily able to do this with our linear CI model. And distributed optimization is both privacy-preserving for sensitive data, and it can retain decision autonomy for these DERs that are privately owned. So with that, I just want to say thank you for the continued financial support from UI Assist. And we will be, we have a manuscript that's been accepted to the PES general meeting this year. And so hopefully we'll be able to see folks in person there. Thank you for that. And I'm happy to take questions now.
Great job. Right on the dollar right there, right on the 19 minutes. Thank you, Rabab. So we have some time for some questions. We have a couple questions in the chat. The first one is it different from the predictor corrector approach?
So I'm assuming that is talking about the regularization in PAC. So PAC is using one approximal term here, and then the regularization that it's using is that one of them is a predictor corrector here. And both of these combined basically allow us to use larger step sizes when we're doing essentially our kind of gradient updates. So both of those combined are kind of some of the unique features of PAC on top of the privacy preservation here. I don't know if that answers the question. If there's follow-up, I'm happy to address that as well.
Great. So the next question is, what is the communication rate of data required to implement this distributed optimization? Can you give some examples of such measuring or sensing devices?
Mm-hmm. Yeah, that's a really great question. So a lot of our work within the distributed optimization framework and all of the other kind of distributed optimization and control for power systems is really requiring on that future kind of system where you have communication infrastructure that's built throughout between different agents. So that's where the idea of kind of the Internet of Energy comes in as well. We have done a little bit of work looking at how PAC could converge for larger systems with some amount of communication delay. And so we have some of that present in one of our publications, so the TSG paper. We have talked about that a little bit in relation to electricity markets. Otherwise, in terms of kind of any other infrastructure you would want for sensing, you could probably be using PMU data and smart meter data to some extent, and you would want some amount of forecasting to be able to know kind of future PV generation, and that's going to help you to use your batteries.
Great. So the next question is, how do you determine the cluster of loads and DER in the 34 node system case study?
Mm-hmm. Yeah, that's a great question. So we started with looking at distributed control, where every single agent, every node has some form of DER and it's its own agent. So there is no amount of clustering happening in the distributed control, and we're looking at the 34 network on its own. When we were looking at local control, the original idea was not to involve some form of clustering. But because we had batteries present, there wasn't really a sensible way to be looking at the objective function of minimizing kind of that power, the power ramping for a battery if there isn't any load that it's interacting with. And for that application specifically, we wanted to create some of these synthetic clusters. So the idea here was that because 26 is a hospital load, 27 was a hospital battery, and so it makes sense for those two to be clustered together. And the rest of them were kind of done in a similar way. Node 6 was a community battery, and so some of the residential loads around it were coupled together. And then here 19 was a Tesla Powerwall, and you could kind of think of different case studies that we've seen in application where a school and, say, a neighborhood are sharing a cluster of batteries. So some of it was informed by different articles. So the community battery is actually based on one of the systems out in Australia. To be able to create a more realistic test case, But if you were to say change the objective function for the batteries to be doing energy arbitrage into the market, you wouldn't need to be doing this clustering because they could kind of operate on their own with that objective function.
Great, and we have time for one more question. How does the local demand minimization within each agent achieve global reduction of demand at node 1 substation? Sometimes it's not possible for each customer. Example, peak.
Yeah, that's a really great point. And that was basically what underpins the need for distributed control. So if you have every agent making its own local decision, then it's only really able to know what's happening locally, and it isn't able to leverage the support of other devices. So if you have a local peak that's going to happen and you don't have much kind of flexibility in that load, there might be another resource that you could leverage at another point, say a battery a couple nodes down in the network that could be leveraged. And so that really points to the need for distributed control in this kind of bulk system level service that we're trying to provide from DERs.
Great. Thank you so much for kicking off our session. Really appreciate it. Rabab,
absolutely. Thank you.
you might put your email in the chat, just if anybody wanted to follow up on your talk. But thank you very much. We appreciate you kicking us off, especially on the East Coast. It's a little later for you than it is for us on the Pacific, in the Pacific time zone. All right, so our next talk will be by Arun Kumar from Texas A&M. So I'm going to turn it over to Arun.